Hey there, boys and girls. Thought we could go on a bit of a road trip today in physics class. That we can't, because it's lockdown. Never mind. But the wheels are still spinning. You can do some research on the miracle of the differential to work out how that can happen. So, what you can see here, classic example of rotational motion. Talking about something rotating doesn't need to be moving linearly at all. It can be sitting on the spot like this wheel, just going around and around and around. And so we're going to have to come up with some parallels for linear motion in terms of rotational motion. What do we measure when we're doing linear motion? We measured stuff like distance and time and speed and acceleration and momentum and kinetic energy. We have all these inventions that we used for linear motion. We need to think about rotational motion. So when we're talking about the very most basic thing for motion is the distance travelled, right? Distance travelled, but it's not moving. Well, it's moving, but it's not moving. What can we measure? What are we going to measure for distance? What are we going to measure for the rate at which that distance is travelling? Hopefully you've spotted that the distance travelled, it's kind of an angle, isn't it? It's turning around and around. And so every time it turns around once, how far is that? 2 pi. None of this degree stuff this year, you stick with pi. So that's 2 pi. And that's going to allow us to make sensible comparisons between linear distance and rotational distance. If we measure our angles in radians rather than in degrees. And so when it comes to talking about speed, we're going to be talking about the number of radians per second. Except that it's just per second, because radian, well, it turns out there's no such thing. A radian is just the ratio between the arc length, like the distance travelled around the edge of the circle, and the radius of the circle. That's how we measure the number of radians. Arc length over radius. And so when it comes to the distance, there's actually no unit for distance. It's just a number. We're talking radians though, but there's no unit for radians. And when it comes to speed, we're talking about radians per second, angle per second. It's just per second because radians has no unit. And for angular acceleration, the same thing plays out. Radians per second per second. What's that rate of change of speed? And so once again, it's just going to be per second squared. We're going to have some new symbols we're going to have to use to represent those 3 quantities, and we're going to have to be comfortable transforming back and forth between angular and linear quantities. And to cap things off, remember those equations of kinematics? Those kinematic equations also apply unchanged to rotational motion. We're just going to have to use new symbols for the new quantities. Let's have a go at writing this down so that we can learn these new symbols. Save some carbon fuel while we're at it. Okay, so let's have a chat through some of these new quantities we need to introduce. That first one, the angular displacement, you can see we're going to stick with the standard symbol for angle, the theta, and we're going to measure in radians. Let me remind you though, that is not a unit. not a unit, and your maths teachers told you it is. Well, they're wrong. Look at this. Circumference is 2 pi r. You all know that from day one. Circumference over radius, we can rearrange to make that equal 2 pi. What's 2 pi? That's the angle. That, in fact, is the equation for linking our linear distance around the edge of a circle, the arc length, with the angle. The arc length divided by the radius is equal to the angle. Arc length measured in meters, radius measured in meters, meters over meters, no unit. There's no unit for radians. Don't let anyone tell you otherwise. Sometimes even in the exam they do it wrong. Then, moving on to how fast something's rotating, the rate of rotation, we're going to call it the angular velocity. Symbol, that funny curly looking thing over there, is a lowercase omega, and the unit for angular velocity is per second. We're talking radians per second, but radian's not a unit, so we just write per second. And if we want to connect the speed of a point on our rotating object with the rate of rotation, v over r equals omega. These equations are on your formula sheet. And finally, angular acceleration, we can see that it's measured in per second squared, same argument as before, and a very similar equation to link our angular acceleration with our linear acceleration. Now we're going to have a look at comparing linear kinematics with rotational kinematics. Just hold fire a second while I sort that out for you. Those are the very familiar looking linear kinematic equations. Unfortunately for you, they're not on the formula sheet this year. Those are the less familiar looking equations of rotational motion. Now, as long as you're fluent in matching up the symbols for rotational motion with the symbols for linear motion, you can see that they're identical equations, where omega is the rate of angular velocity, the rate of linear velocity, the alpha is acceleration, a is acceleration, theta is distance, d is distance, t is always just time. So as long as you're confident in matching up those symbols, then you can create those linear equations from the rotational ones that are on your formula sheet. Now, I'm not even going to write it down, but as we talked about last year, with acceleration equals speed over time, they're going to try and trick you again this year with the same ridiculous equation of angular acceleration is angular velocity over time. It's work of the devil, don't go near it. What's next? I hear you asking. We're going to have a chat about Newton's laws.